this video we're discussing the Kruskal-Wallis H-Test. The Kruskal-Wallis H-Test is analogous to the Completely Randomized Design ANOVA procedure we learned earlier on in the course. That means the data will be basically the same kind of data. So remember what we dealt with in that type of experiment is we had 3 or more independent populations sampled, and then we applied a treatment to each sample, and those treatments were then compared based on the treatment means. We wanted to see if the treatment means were all the same or if they were different. So we're doing the same kind of thing here. We're going to have 3 or more independent populations sampled, and we're going to have a treatment applied to each sample that we take, and then we're going to compare them. Instead, we're going to be comparing their population medians, though, and not the population means, right? Because it's a non-parametric procedure. But basically, the idea behind the data is very similar. We have one little condition here, which is going to be important. That is that we need to make sure that we have at least 5 measurements in each treatment. So in other words, this list of things, I put ... but this has to have at least 5. It can't have less than 5. B would have to have at least 5. C would have to have at least 5. But here's an example. Let's imagine that these examples are essentially, let's say they're samples from different sports, and we have, for example, say basketball players, soccer players, and football players, American football players, and we're looking at their long jump scores. So maybe somebody wants to know if there's a difference between the lower leg power of these different athletes. So we're recording their long jump distances for each sport, right, from a random selection of members of each sport. Okay, now at that point, once we have those different scores, the distances that were recorded for each person who took the jump, and notice that the distances are also continuous, right? So we have 8.1, 9.2, right? We have any possible decimal distance in their jump. That's an important part of this procedure. But aside from that, the next thing we want to discuss is the fact that the way we're going to handle this data is that we're going to treat it all as if it's one large sample at first. So this is kind of analogous to our Wilcoxon rank sum procedure. The Wilcoxon rank sum procedure was when you dealt with 2 independent populations, right? If you remember what you did, you ranked all the data and then you summed up the ranks for each separate group, right? It's the same thing here. We're going to rank all the data, right, as if it was one big sample. And then when we're done, after applying all the ranks to all these numbers overall, then we're going to again separate them again and just add up the rank totals for A, which would be the rank total 1, right? So the first rank total. Then we'd add up the ranks for B, so it would be rank total 2, and then add up the ranks for C, rank total 3. The logic of the test is pretty simple, right? Again, if A, for example, has all the big scores, if the basketball players have the most power in their legs and they can jump the farthest as a result, they're going to have all the long or the high numbers for their long jump distances. That means they'll also get the corresponding largest ranks. So when you total their rank total, it's going to be higher than the rest. That would be the idea. And of course, we would see if there's a significant difference between those rank totals based on that. So that's kind of the idea of the procedure. It's a pretty clever idea. It's very similar to the Wilcoxon rank sum test. It's just expanded out to multiple populations. So you can go to 3 or more populations now, not just 2. And then here's overall the structure of the hypothesis test and procedure. Of course, we'll see the mechanics worked out for these specific examples in the problem videos, but here we have the null hypothesis says the k medians for the probability distributions are identical, so all the medians are the same. This is like in the completely randomized design hypothesis we had, all the means are the same. Here we're saying all the medians are the same for the probability distributions of these 3 groups, right? If there was more than 3 groups, we would have 5, 6, 7, 10 groups, 20 groups, K groups. K, remember, is the number of treatments that we have. All right, then HA is at least 2 of the medians differ from one another, so at least 2 of those population medians are not the same. All right, and then the test stat for the procedure is a complicated formula, but it's not that hard. It's just a mechanical thing. You plug in the numbers and work it out, right? So, of course, this is a constant 12, n times n plus 1. This n is the overall total number of values you have, the overall sample size. So that's n then times n plus 1. Then you have this summation. So what this is, it's the rank totals that you had for the treatments. You square each of them, and you divide each of them by the total sample, not the total sample size, pardon me, but the sample size for the individual treatment. So for example, if this had 5 scores in it, and the rank total was 20, you would have 20 squared divided by 5. And then you'd add to that, let's say this had 5 and the rank total was 30, you'd have 30 squared divided by 5, and you'd add to that whatever the rank total was here squared divided by its sample size, right? So the individual sample sizes are these little NJs, right? And then from there you have minus 3 times the overall total sample size plus 1. And then once you're finished with that, you get this test statistic H. It turns out that that test stat will have a chi-squared distribution, which means our critical value will essentially be a chi-squared value. And we know that table pretty well. It's very easy to use. So we'll compare our test stat to the chi-squared critical value, which of course will be based on some significance level, and k minus 1 degrees of freedom. In our example here, we have 3 minus 1, or 2 degrees of freedom. We'd have some alpha that would be given in the problem. We would compare our test stat to that critical value. If our test stat is large, it'll be considered significantly large, and we can reject the null hypothesis that they're all the same, and therefore support the idea that at least 2 of these can be matched up so that one is bigger than the other. And that's it. So that's essentially the idea behind the Kruskal-Wallis H-Test. It's a really nice alternative to the completely randomized design ANOVA procedure. Just remember this little issue here, though, that you want to make sure that you have for each treatment a sample size that's at least 5. The other little detail that you have to pay attention to, of course, aside from the normal conditions that you look for in the completely randomized design idea, which is that they're independent samples, but we also want to make sure that the data itself is continuous, so measured on a continuous scale. If you meet those 3 conditions, the Kruskal-Wallis H-Test can be used.